one who steals most of the things from my office, so that's fine. Also the person who approached my son and asked him in Berkeley whether he knew what a diamond cell was, and what ensued was a very interesting conversation between two kids who knew what diamond cells were. But anyway, so Zach Chappelle, is that right? Jabal. For those of you who don't know, has a great lineage. His grandfather measured the specific heat of copper, and it's a seminal paper. And so Zach came to this lab after getting his bachelor's in physics and a PhD in geophysics from Berkeley to measure the specific heat of copper in a diamond cell. Except that he keeps using gold, and I keep thinking that that's why he's called Goldman Sachs. But I'm sure at the end of today's talk, we'll know if it's Goldman Sachs or Goldman Sachs. Take it away, Zach.
Thank you, Lou. So thanks for that introduction. That was funny. And thanks to George for inviting me to invite myself to give this talk. And thanks for everyone who came. I'm going to tell you what I've been working on for the past 2 years. And I'm going to show successes and failures so that you can see what not to do and what is needed to make heat capacity measurements at high pressure, or calorimetry measurements. And I'm going to tell you a lot of engineering, but to motivate that, first I'm going to tell you many reasons why it would be interesting to have a way to measure heat capacity, latent heat, thermal conductivities of materials at high pressure. There's motivations from geophysics, from low temperature physics, glass physics, so I'll touch on a few of those different areas and then get into what actually I did in the lab these past few years. So first of all, what is calorimetry? So calorimetry is a measurement technique that the experimentalist puts in heat and measures how much the temperature changes. So the amount the temperature changes can reflect the heat capacity of the material, it can reflect the latent heat across a phase transition, it can reflect the enthalpy change during a chemical reaction, or how fast heat is transported out of the sample chamber. So let's take a look at one of those more specifically and see what do we expect. What kind of information is gained from making calorimetry measurements. So here's the definition of heat capacity here at constant volume. Heat in divided by the number of moles where the heat is deposited divided by the temperature change. So the units are joules per mole Kelvin. And for 4 different simple materials, lead, silver, aluminum, and diamond, we see that, so say, just imagine this temperature, whatever that is, 40 Kelvin. The heat capacity of lead is this value, and it's telling you how much heat is needed to start exciting the vibrations in the lead, because that's how the temperature increases. But the heat capacity itself is actually changing as a function of temperature, and that's because at low temperature, materials, there's vibrational modes that aren't excited, whereas at high temperature, all the vibrational modes are excited. And with increasing bond strength, going to very strong, very tightly bound materials like the carbon atoms in diamond, the heat capacity gets much smaller at fixed temperature because more and more temperature is required to liberate kind of these degrees of freedom, at which point then they contribute to the heat capacity. With pressure, how would this change? Well, if everything was so simple, like in this picture, all these curves would just shift to the right because bonds get tighter, so more temperature is required to access those same degrees of freedom. But not everything's so simple. So here's something that's not simple, water. So the heat capacity of water, or ice, then water, then steam at ambient pressure is shown here in the black curve. And it kind of goes right through this classical value that I've shown as a dotted line, which is, by the way, that's 3R, or 3 kBT. Instead, the heat capacity of ice goes up higher. Then water has a huge heat capacity because hydrogen bonds require lots of energy to bend. So every degree Kelvin increase for water requires a lot more heat than other materials. And then it drops down for steam. So that's just one example. That's just kind of a primer on what is heat capacity, how to understand that basic property. So why bother to develop this at high pressure? I think the simplest reason, it's kind of abstract, is that it's a basic thermodynamic quantity that hasn't been explored much. The one you're more familiar with from high pressure studies, from what most people talk about, is how hard is it to compress a material. So that's kind of going along the pressure dimension, and if you like, the Gibbs free energy, the second derivative of Gibbs free energy with respect to pressure is related to the bulk modulus, whereas the same thing, but in the temperature dimension, is equal, well, times T is equal to the heat capacity. So that's kind of abstract. What more specifically do I think we could learn? So now I told you I'm going to give lots of motivation. So I hope that it excites people from different fields to see how heat capacity could be useful. So actually, Einstein showed that, interpreted heat capacity data of diamonds to come up with his quantum theory of solids. So all that description I showed you on the first slide of how diamond's heat capacity increases slowly from 0, I think over here is like 1200 Kelvin, showed early condensed matter physicists that that vibrations are excited more and more as the material is heated up. I don't think that's going to break down at high pressure. So it's not like we're going to prove them wrong. But there's new possibilities. Like one set of proposals from researchers recently, and maybe going back a few decades, that has very little experimental testing, is how does the heat capacity change from the classical limit of 3R, here's 2.8 R, down to the ideal gas limit of 3/2 R. And there's some theories of how that would happen, how that would relate to viscosity and shear modulus, but they've largely been untested because of lack of data. Another reason is for planets. So a lot of people here are interested in modeling planets, both the Earth and other planets. So I'm going to talk about water. So I'm showing here simple models of the interior of Neptune. Uranus looks similar. Here in this triangle is a simple model. Here in this triangle is an even simpler model where we assume Uranus is all water. But even for a pure water planet, there are phase transitions where that have been like researched by Alex Gontrov and other people have found that molecular water becomes somewhat conducting and then really maybe more conducting in a sort of exotic state where the hydrogen atoms are free to diffuse within an oxygen lattice. But the energetics of how this happens and the details are largely unexplored. Unfortunately, these pressures and temperatures are beyond, here's the temperature from 1,000 to 8,000, are beyond what I can measure now. So this is kind of really future work. But at lower, here's the phase diagram of water. It's much more complex than just, it's pretty rich already, just in the interiors of Uranus and Neptune. But the phase diagram of water, temperature as a function of pressure, this is a log-log scale, shows all these different phases of ice. And this is just the equilibrium phase diagram. So there's also glassy water, lots of things to study in water. So zooming in on this lower pressure temperature region that's accessible by my current techniques, there's plenty of satellites and even the Earth, subduction zones in the Earth, for which heat capacity data doesn't exist. I mentioned glass transition. So I'm interested. I haven't used heat capacity to study the glass transition, but that's one of my biggest goals, because heat capacity measurements historically showed actually that there's a residual entropy in glasses and help describe the third law of thermodynamics. More recently, for decades, there's been debates about how to describe the glass transition in water using heat capacity data, but I don't have time to get into that. Another thing, I'm starting to study superconductivity, and I recently learned, Ajay pointed out to me that heat capacity has been important in describing the transition now of electrons. So I was talking all about vibrations, but heat capacity is also sensitive to electrons. So when electrons go from superconducting to not superconducting by killing the superconductivity with a magnetic field, there's a heat capacity signature, which showed people that there's an energy gap, and that's one of the interesting properties of the superconducting transition. So I think that's enough motivation. To summarize the motivation, here are the 4 things I mentioned, and then just the general idea that heat capacity is a fundamental property that hasn't been explored at high pressure. So how bad is the situation? Well, here's kind of here's kind of where data's been collected. So at low pressure and all temperatures, there's tons of data. Really, everything I showed you so far is ambient pressure, or maybe up to like 1 GPa or 2 GPa. There's shock data that is fast and destroys everything, but they make pioneering measurements on dramatic changes in materials. But they have their own experimental challenges. And actually, most shock data don't really measure heat capacity, but recently there's been some that do. And then a set of interesting data up to about 10 GPa and 20 Kelvin showing how heavy fermion compounds change with pressure and looking for like quantum critical points. I don't really know much about that. So, there's huge region of phase space for every single material unexplored. So why is it unexplored? Well, it's unexplored because it's challenging to make these measurements, as I've learned. No, I knew it would be challenging, and now I'll tell you why, and then I'll tell you what works. Okay, so here's a static high pressure cell. In this case, a diamond cell, because that's the static high pressure device that can generate the highest pressures, the pressures of the Earth's mantle and core. So here is a blue diamond, another tip of a blue diamond. Squeezed between it is some metal that provides lateral confinement, a sample, and some surrounding material, all schematic. The first challenge is that this is small. So the diamonds squeezing on things makes them thin. So that's the first challenge. The starting thicknesses we use are maybe 30 microns. Maybe they start at 50 microns, but pretty quickly everything gets thin. When Zulu does experiments, they may end up at 2 microns thick. So it's really small length scales. The small length scale then requires a big problem for calorimetry measurements. Because remember, calorimetry is heat in, temperature out. The problem is the heat diffuses quickly at short length scales. So here is shown schematically that in 0.1 milliseconds, the heat would diffuse most of the way to the diamonds. In 1 millisecond, it would get into the diamonds and then get diffused away, because diamond's a great heat sink. And then the third problem that I've appreciated more since actually doing this is that when we squeeze on things, there's a lot of shear stress. So a lot of things can break. So first let's address these first two challenges. Why did I ever think this would be possible? Well, I modeled it in my PhD, and that's when I talked to Zulu's son, was how do I make this electrical measurement? So if we connect this red sample that's squeezed between the diamonds to electrodes, and then looking kind of obliquely at the tip of the diamond, we use a power supply to run current through a circuit, measure the current, how much current's going through, measure the voltage drop, that'll tell us how much power is deposited, and somehow we measure the temperature in the sample chamber. That's the idea. That's schematically. Does it work like with typical material properties, typical thermal properties of materials? Taking an iron sample and I think this is KBr insulation, with diamonds 30 microns apart, one temperature oscillation, the temperature profile would look schematically, would basically look like this. This is a real calculation, but it's shown in kind of a weird way. The temperature would oscillate up and down, hotter and colder. If we oscillate temperature at 10 microsecond time scale, then most of the heat stays in the sample chamber. If we do it even faster, all the heat stays in this sample. So this would be a really ideal heat capacity measurement. And this is why, even though the diamonds are a horrible heat sink, that calorimetry is theoretically possible in a diamond cell. Then I came here and started seriously working on the experiment. So the first thing I did, the first strategy, was to measure, to do exactly what I showed in that schematic. Put a piece of metal foil, cycle current back and forth through it, and measure the temperature change. And see, can I measure the heat capacity of this piece of metal squeezed to high pressure? So this is platinum heater. It's the heater, it's a thermometer, it's a sample, and it's squished to 2 GPa. So did it work? Well, okay, no, that's not the question yet. First, then I connect it to electronics. So I'm talking fast, huh? Okay. so I'll talk slower. So the schematic electronics look like this. The first key step in the design is a power supply, electronic power supply, that drives current through the sample to ground, to zero potential. There's some resistor here as kind of a reference, and then it's a sine wave of voltage. So if I can measure the current through and the voltage across the sample, I can use P equals IV to know how much power is deposited. To estimate, to measure heat capacity, I need to know the frequency that I'm driving the current at and the volume of sample. So those are kind of normal things to measure. How big is the sample, what's the frequency. I also need to know the amplitude of the temperature oscillation. So now I need to explain to you the most complicated thing, part of my project, is how to measure temperature. This sample is tiny, so putting a thermocouple next to it would not measure the heat capacity of the sample itself. It would measure something else. So instead, I've learned about this thing called the third harmonic technique, or 3 omega technique. So it's a little tricky, but it's pretty, I think it's powerful, and it's been used at ambient pressure. So I've adapted it to high pressure. If we drive current through the sample at some frequency, here it's 10 microsecond period, that causes the voltage to oscillate at 10 microsecond period. Multiplying these two gives a power. The power has a DC offset, like an offset, some constant power, and a second harmonic, higher harmonic of power. That drives the temperature up and down, which causes, luckily, a change in the electronic property of the heater. The resistance changes by a little bit at the same period. And that resistance then is basically measurable because it induces a new voltage, a third harmonic voltage. So to read this, you have to remember sine multiplication rules, and the final step is sine of 2 omega t times sine omega t has a cosine 3 omega t in it and a cosine omega t. So that's what's shown here, is that there's third harmonic and a first harmonic in some new additional voltage. But how to measure that voltage? Here's back to the schematic. Driving current through here, there's two voltages across this sample. There's the primary one that's being driven by the 10 volt sine wave, and then there's the one on top of that. So by taking another circuit, just with two off-the-shelf resistors, and then a differencing amplifier, outputting that, then I can possibly measure that this kind of dynamic resistance change, which tells me how much the temperature is changing. Okay, so that's the third harmonic technique. That's the way to make a heater, both the heater and the thermometer. Does anyone want clarification? Yes, Zhushua.
Why is the resistance change in temperature?
Because most metals, pure metals, have a few part per thousand change in resistance per degree change in temperature. Because as you heat up a metal, there's more and more vibrations. Electrons collide with those vibrations. There's some horrible alloys that don't do this, but I chose to not use those alloys in my experiment. And other little clarification. Okay, so then does this work? Well, I make some ugly circuit. I make a measurement. Oh my God, here's the voltage in, and here's the voltage out on this oscilloscope I first used. So it looks good, right? It kind of looks like the model, but I don't know. It's a little hard to see. How do I validate whether this is real? I vary the frequency. And now here's the data and here's the model. And so obviously this didn't work. Okay. But so take a step back. Is this third harmonic technique actually possible on the short length scales of diamond cells? Don't worry, the answer is in some cases yes. So it's not all bad news. So I took a step back, put a strip of iron between glass slides, not inside a diamond cell sample chamber, but still pretty short. Make measurements. Now I got a new oscilloscope. And wow, okay, this really has that nice shape that has the 2 different harmonics. And this is real averaged time trace, like voltage as a function of time averaged over 100 cycles. Here's the driving voltage, so it's higher harmonic generation. Now when I vary both frequency over from 10 hertz to 100 kilohertz, and I vary the deposited power, I see much more systematic behavior. I run this through the equations that tell me, that kind of go reverse the process of taking that 3rd harmonic voltage, here converting it back into the temperature, because the temperature change is what caused the 3rd harmonic voltage. There's Gishui's question, is alpha is the temperature coefficient of resistance. And then I infer, that tells me how much the temperature is oscillating. Then I use the equations of calorimetry, and all the data plots on one curve. So that's encouraging. How to interpret this curve? The measured heat capacity is changing as a function of frequency. So that's not physically reasonable. That means this measured heat capacity is not the material property I want. But instead, I can kind of model it with a few different models and see that at least it's reasonable. At least the measured heat capacity follows some reasonable picture of what I showed you at the beginning, which is that at long time scales, heat diffuses far into the volume around the heater. Dan?
So I just have a quick question out of curiosity. Why is there this narrow frequency range where the error bars are much worse than at all the other frequencies?
Good question. I don't know. I'll show you other data where it wasn't quite so true. I don't quite understand the spurious signal in my circuit. I understand it roughly, but not quantitatively. So I mean, okay, there is an answer. Harmonics can be generated many places in a circuit. It can be generated in the place I want it to be generated, which is at the heater, or it can be generated in the amplifier, in electrical contacts. So the frequency dependence of each of those potential sources of harmonic generation is mysterious. Yeah, Steve?
Are you using a reference voltage?
What's that?
A secondary reference voltage, and then comparing the 2 voltages against each other. You should be able to subtract out any non-specific harmonics if you use a reference voltage.
Yeah. I am, kind of. But I'm measuring like at 4 orders of magnitude lower voltages than my input voltage. So it's pushing to the limit of these electronics. They're pretty harmonically pure. When I use a reference, I get even better signal to noise, but there's still some spurious signal that's not symmetric. So I can understand this data qualitatively, and it has a potential future, but this isn't the direction I headed, because I was too disappointed that I couldn't make robust quantitative measures of heat capacity of metals, and I had a better idea. So okay, first I did this. I tested on other metals, then I did some error analysis and figured out that the 2 different waveforms coming out of this wave function generator are not perfectly don't have exactly the same spurious harmonics in them, and so some upgrade of electronic devices could reduce these error bars. But here's a different strategy. Forget trying to push electronics to fancier and fancier. Let's use what we have, but study something else. Rather than studying metal's heat capacity, I want to talk about water's heat capacity. So here's a metal strip heater. It's platinum again. It's both the heater and the thermometer, but now I'm not trying to study the platinum itself, I'm trying to study the surrounding medium, which is water. And this is at half a GPa, I think. I make the measurement, wow, okay, now I'm showing kind of all together. The driving voltage is in black, and then this harmonic, which is much reduced in amplitude, even after it's been multiplied by the gain, shows these higher harmonic oscillations. Vary frequency, vary amplitude, kind of a mess, so this isn't an ideal setup yet. Process it through equations. Now I'm not really measuring heat capacity, but something called, I called it thermal conductance. But it's related to the ability of the water to suck heat away from the platinum. That's what I'm measuring. hopefully I can interpret that in terms of material properties, and I'll show you why it's possible to do that. But for now, it's really qualitative. So as a function of frequency, the data kind of collapses to a line. That's encouraging. So I put this cell in a low temperature in a cryostat, which can vary the temperature to low temperature and back to room temperature, and measured the freezing and melting of water. This is my first real data, kind of. So dropping the temperature in this blue curve, this thermal conductance, the ability of water to suck heat away from the platinum, decreases and then whoop, jumps up. Then upon heating in red, it drops down. Upon cooling in teal, it jumps up at almost the same place, and then in heating, what I interpret as melting is at the exact same point. So very reproducible, quite low pressure, but still exciting for me. I can check, because this is electronic measurements, so one nice thing is you can really check what's happening to the heater, and the resistance is cycling in a pretty systematic way with some hysteresis related to the uncertainty in the temperature measurement, but nothing like the hysteresis I see in the freezing and melting of water. And I can actually, in this low pressure case, you can actually see water crystals forming and melting. So I can visually confirm that. Higher pressure, the data quality got worse, and then the crystal phase transitions in water weren't possible. So back to experimental design. Two more times, and then I promise it's over. So a better design than that platinum strip would be a really, really thin piece of platinum. Maybe I shouldn't try to explain why, but you'll see the data. So here's a thin piece of platinum that's getting pushed between glass. It's at 0 pressure, but there's good electrical connections. Pretty ugly, but the data looks good. So here's the higher harmonic generation from the temperature change of that platinum, and when I vary frequency and amplitude, I get really smooth curves that then I run through the equations, and they collapse to a curve that now actually seems to approach a single value. So in this case, this ability of the glass to suck heat away from the platinum is telling us the material property of thermal conductivity times heat capacity, and if you like square root, well, okay, it's approaching the square root. That has a name. That's called thermal effusivity. It's the ability of a material to suck heat away from an interface. So that's actually what I measure. And one day, there are known ways of how to deconvolve these two material properties. So one day I hope to do that. So then the final step is to replace the glass with water and compress it. So it's simple in theory, but this took me a really long time because making connections to this platinum was 50 nanometers thick. Eventually I figured out how to make a connection to a 20 nanometer thick coating of gold on glass and squeeze it in a way that the whole circuit doesn't break so that I can make these electronic measurements. Why is it so challenging? Primarily because of length scale. So here's about 5 millimeter size scale bar. So I've already cut copper strips. So who wants to know why I'm not studying copper? Down to pretty small, but now I need to connect them to this thin film and compress it. So I'm going to show you some failures now. So how not to do this, unless you're really more skilled than me. So, but you'll see a lot of these methods just don't apply to high pressure experiments. So one idea is just, why don't we just use the water to kind of push metal into metal? But stuff moves. Okay, another idea, put more metal, try harder. There's little copper blocks. Push the gold into the copper, into the gold thin film. And here I made some fancy, really fancy heating strip. And there's, I think those are bubbles of water. So it's about to be compressed. It all looks good. Everything kind of crumples. So I think at this point, Zulu told me, there's too many things moving. You gotta fasten things down somehow. And Victor and I were like scratching our heads, trying to figure out what to do. We tried mica. We tried more mica. We tried more mica. because mica was tempting. It's like it bends, it doesn't break, but the problem is, even though it doesn't break, it breaks the circuit. Then we tried silver epoxy. So I cured silver epoxy, which is glue that has little silver particles in it. So it's a cool material. It's kind of a mixture of, has a bonding strength of the glue, but the silver particles polymerize. George tried to explain to me what happens, and make metallic bonds. But then when you squeeze on it, in my experience of like 6 times trying, the contact resistance, the resistance between this strip of gold and this gold thin film changes even with time, because it's not a real metallic bond. Emma showed me how to use the fib to deposit platinum, but again, the contact resistances were way too high for my purposes. I looked in the literature and found that people have actually deposited metal thin films, coated those with diamond, then done experiments, but the films are too thin and the lead resistances are similar to the resistances of my whole circuit, of my whole heater. So with typical designer diamonds, this isn't possible either. Uh-oh. Don't despair though, because sometime during my months of struggling, George allowed us to buy a micro manipulator, a very fancy new machine that I mess around with a lot and continue to mess around with, and I figured out how to make it solder. So I polished a piece of aluminum, put it on the soldering iron. The machine shop made me this holder, and eventually I figured out how to melt solder, at least some of the time, in a way that the platinum connects with a metallic bond, metal, 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 to the gold thin film. And now I think this is a great electrical setup, because the resistance of these leads is like less than an ohm, maybe 0.2 ohm, 0.1 ohm. The resistance of this is 22 ohms, so all the power will be deposited at the center of the diamond cell. I think there's no contact resistance. Anyway, so I put water in the cell, and I close it down, and it held pressure, and the resistance was 22 ohms total resistance from this side to that side. So then I could use my same circuit that I had developed, run current through it, measure these higher harmonics of voltage that tell me the temperature is changing. I never showed you before, if you like, in Fourier space, the driving voltage here was at 10 kilohertz frequency, and the measured voltage is both at 10 and 30, with some noise that's a factor of 30 below the signal, so it's really high signal to noise data. Vary the frequency. There's some curve that one day I'll be able to interpret, but right now I don't think it's really worth trying to model the exact curve. More or less, I can just take some point at this high frequency region and assume that reflects qualitatively the ability of water to suck heat away from the gold. I vary the temperature upon cooling, boom, freezing. No more phase transitions down to low temperature. Upon heating, something bad happens electrically, and I can't tell where melting is, but I can confirm my measurement from before. And I kind of trust this experiment more because it's such a thin heater, so I can interpret this as the sign of the change of the thermal effusivity at 1 GPa. Oh, I mislabeled that. So at 0 GPa, there's plenty of literature. Ice 1H has a higher thermal effusivity, ability to suck heat away, than liquid water. At higher pressure, now I'm seeing the opposite transition. Is this real? Well, there's some data up to high pressure. Okay, so it could be true, because the ice 1H transition, ice 1H has a higher thermal conductivity, because this is the kind of calorimetry data that existed at high pressure. Up to 2 GPa, thermal conductivity, ice 1H has a higher, it's good at sucking heat away, whereas these other polymorphs of ice aren't so good. But more data. So exact same setup, slightly different end result. I vary the temperature, amplitude, frequency. The temperature scans show now at 6 GPa, so higher pressure. Ice is totally solid. going from room temperature down. There's a step function change up during cooling in blue, and a step function change down, heating in red. This corresponds to what people have seen and identified as a transition from less ordered ice at high temperature to more ordered. The protons now are ordered in an ordered arrangement between oxygen atoms, whereas here the hydrogen atoms are disordered. The oxygens are still in a periodic arrangement, but the hydrogens aren't. And there's some hysteresis. So I don't think people have systematically measured the hysteresis. And I did it at 6 GPa. I repeated it. It's very reproducible, the position and temperature of this transition. At 9 GPa, I can measure it. The hysteresis loop gets a little bigger. I can plot these on previous phase diagrams of water to show that my technique really is detecting equilibrium phase transitions. And I can start to investigate the kinetics of the reaction, because I can just click go, leave the cryostat cycle's temperature, and I can measure the hysteresis loops. When I do 8 Kelvin per hour versus 2 Kelvin per hour, the size of this loop, the cooling versus heating, phase transition temperature, diminishes. So this is preliminary, but I can plot those on a transition, the rate at which the transition happens versus inverse temperature in an Arrhenius plot, and put a line through it corresponding to an activation energy of 0.9 eV, and predict that if I measure at much faster rates, faster rates up, that the needed temperature will be higher to get to this disordered state. But actually, I don't really want to predict that. I want to make the measurement, because this is proton ordering, disordering. So there could be more exotic things, like the protons, the hydrogen atoms, can tunnel over energy barriers. And with tunneling, we expect a change in slope. At low temperatures, it doesn't matter. The protons will just tunnel. They don't need the thermal energy. And I've built a way to study this once I get a new sample loaded. So now I'm to work in progress, which is that I have a new circuit board that I can use to increase the power steadily, increasing the background temperature, and here, in this case, over 30 seconds rather than like 5 hours, traverse a phase transition. But I gotta show that this works with a real circuit, because I failed the first few times I tried. Other work in progress is to measure the absolute value. Tim, that was going to be your question. I'm sorry. Okay, so to measure the absolute value of heat capacity, I need some really fancy circuit. So here I've done lithography on the gold thin film, leaving just a thin strip of gold and connected 4 leads to it. This particular loading didn't work, but I think I know why. I've actually made the micromanipulator look much cooler. So this is a picture from the micromanipulator, and be much more effective at melting solder. This is a tungsten needle, and this is a piece of platinum that I've cut and mounted on the other arm of the manipulator, and now it's glowing. So it's like 1,000 Celsius, and it's heating the tungsten needle, and then I can move both the heater and the needle and push into solder. So that might seem extreme, but I can show you that it's needed, because making electrical connections at the 10 micron scale is difficult, because surface tension matters, surface oxidation matters. Those are the things I want to do in the near future. And then Kadek and I have started a collaboration that's much more general than just heat capacity. We're trying to make designer diamonds like the other groups have, but in our own way and with new features. So I've deposited titanium on diamond, and now he's grown diamond on top of the titanium. So it's diamond, titanium, diamond sandwich. And he's trying to make nanocrystalline diamond for thermal insulation. Really fancy things that hopefully one day will open up opportunities to measure heat capacity at really high pressures, and to make electrical transport measurements at high pressures, things like that. And then finally, Zach Whitlock, who's here, is a great high school student who's come to build a new type of electrical measurement, and he's already shown that we can at least reproduce what off-the-shelf electronics do, and now This week he's testing, can we go beyond off-the-shelf electronics to try to measure the dielectric constant of things like water at high pressure using the same kind of circuit. There's a reference resistors and then the sample capacitors. So we'll just replace one of those capacitors with a diamond cell and everything will work. No, but there's possibilities to actually measure the dielectric constant of water. And Victor and I started talking about this after Julia Galli showed her exciting theoretical results on heat dielectric constant of water at high pressure. So to conclude, I've shown that the hysteresis of melting of H2O can be quite large, and that the hysteresis in this order-disorder phase transition varies with the rate, maybe in an Arrhenius manner, maybe not. But those are kind of small scientific contributions, and really my contribution, I think, is developing a technique. So I've shown that this thermal conductance can be a sensitive measure of melting of proton order disorder, and I think that shows that it can be a sensitive measure of all sorts of phase transitions. And the real key to making this research scientifically meaningful is to make this reproducible quickly, so that you don't need to spend like months in the lab to get one cell loaded. But with the micromanipulator techniques I'm working on, I think I'll show that I can actually do it reproducibly. And I've shown a negative result, which is that measuring a metal itself, which is actually the first type of calorimetry measurements there were just heating something and seeing how much its own temperature changes. But I've unfortunately shown that current technology doesn't allow quantitative measures of those metals at high pressure. So I'm really grateful for the opportunity to do this research, and for these people who have helped me design everything I've shown, because you saw the first circuit I made. So Paul Goldie had to teach me how to put together a good circuit that doesn't change every time you touch it. And Zulu told me what I was doing wrong with the loadings, and together we kept trying new things. And same with Victor, has helped in every step of the figuring out how to load these samples, figuring out how to use electronics, suggesting new ways I could use the electronics. And Nick also helped me with some collaboration I didn't have time to show. And Kadek and Zach and everyone who's given me advice and everyone who's been friendly to me here. And it's been a great place to work. And I'm staying here for a while at least. And for Carnegie for the funding, and the Department of Energy also for supporting the research. Thanks for listening.
Thank you, Zach. Questions?
Yeah.
It seems that the thermal conductance you measured have very strong frequency dependence. And if my understanding is correct, you use literature value to benchmark the frequency region that you're going to measure the thermal conductance at the outer temperatures, right?
Mm-hmm.
Do you know, my first question is, do you know the region frequency dependence? Because usually whenever you have a frequency dependent quantity, it suggests that you have dynamics of different relaxation times.
I'm
Which
sorry,
means
yeah.
it may depend on the temperature as well.
Yeah.
So, have you ever looked at a same plot at different temperatures?
Yeah. So unfortunately, I think all those things are interesting, but my data quality is not good enough to investigate the phenomenon you're talking about. That is, that some materials do have an intrinsic temperature frequency dependence.
So you think this is an extrinsic?
Yes. It's because I called it thermal conductance as a bulk property of the sample chamber. It's a property of the sample chamber, but the geometry of the heater and of the sample chamber is not sharp enough. It's not well defined enough
My concern is the thermal conductance never get converged.
Yeah, I only showed one where it does. The one with the best geometry. Here we go. Come on. This one.
Yeah, my concern is, you need to know the literature value to
As a function of
determine,
frequency?
to determine the frequency you're going to use, right?
Yeah.
Because if you just have this plot, if
Yeah.
you don't know the literature value,
Yeah.
which thermal conductance you're going to use, that's my concern.
Yeah. I would use some average of these. When I try to make, I haven't said anything about quantitative, the absolute value of these intrinsic properties of water. But when I do, I'll use the data itself. These are error bars, and there's some change in the measured value. So I don't want to use the value when the error bar is large, and I don't want to use the value when the frequency dependence of the sample chamber's properties is changing quickly. I mean, it's kind of like we got to bootstrap our way up, because yeah, there's no data at high pressure. So you're right, we can't really trust the ambient pressure values or models to know that the technique is working.
I guess my concern is that this line can
Yeah.
also be temperature dependent. So
Yeah.
yeah. And
It is, yeah, it is, because at low frequencies, it reflects more the thermal link to the outside world, and at high frequencies, it reflects more the heat capacity of whatever is next to the heater. So it is. I've looked at it, and it is temperature dependent. There's not an easy way to say what every kink means. But and some, I thought some like supercooled liquids, upon close to the glass transition, show the temperature dependence of the measured heat capacity. We're supposed to call it enthalpy fluctuations, not heat capacity. But anyway, so there are, sometimes it's real, but this is due to the sample geometry. Yeah, Dan.
So I know in some of these experiments you were showing that you're using really, really thin strips of metal to the point where the thickness is just in the tens of nanometers regime. And I know that for some, I don't know if this has really been done for electrical properties per se, but some thermodynamic properties, there are quantum effects that actually come into play that change the properties themselves just because of you have such a small length scale that it doesn't behave the same way that it does in the bulk. So I'm just curious if there are concerns about that even apart from it being difficult to set these things up at such a small length scale, that the small length scale itself might actually be changing the real conductance and so forth. Is that a concern?
For electrical conductance, it's not a concern to me because these are metals, so they already transport electricity. I don't think surface effects change the bulk conductance of metals like they do for non-conducting materials. For thermal transport, I haven't done enough work to show that it won't matter because there is something called, it's not really a quantum effect, it's called interface conductance, that vibrations in the metal might not propagate effectively through the monolayer interface, through the interface with the surrounding medium. So that's called interface conductance. And actually people have studied it because they're interested for electronics industry. But I think that's a second order effect compared to the heat. That's not where the heat's going. I got to do the modeling one day of where is the heat flow getting blocked. But I'm pretty sure it's in the 10 micron thick surrounding medium, not in the like 5 angstrom interface. Ajay.
Do you like to have some independent method of determining temperature from the sample chamber? And another thing is that, another point is, like, instead of water, suppose you have some nano sample in your sample chamber, like maybe nano diamond or something. The heat capacity, drastic changes for that.
Yeah. Well, thermal conduction will have a drastic change. Like nano diamonds, thermal conductance is similar to salt, to like NaCl. So that's why we want to use that. What was your first question again?
Independent method of determining
temperature.
temperature from sample chamber. Is there any?
There's not many. Because I put a ruby in to measure pressure, assuming I know the temperature. I vary the cryostat temperature slowly so that I know the temperature at the surface of the diamond cell. But if I wait for long enough, I'm confident in those values. When I do these faster heating, when I raise the DC temperature, the thing I'm going to rely on is the resistance of the heater. I don't think there's not much room in diamond cells. So if we put 2 pressure markers, we could put samarium doped YAG, or if you put 2 pressure markers, you can know both the temperature and the pressure in theory, but I don't think those scales are so well developed. I think a metal heater, the resistance of a metal, is a pretty good temperature measurement. Yeah, Tim.
For your preliminary results on I7, 8, what are the units of your activation energy?
EV.
EV for what?
I was thinking about that last night. Yeah, per atom or per molecule?
So it was like 0.9 EV?
Yeah, 0.9 EV.
So if it's like per molecule, maybe that's like 90 kilojoules per mole. I don't know.
Okay.
It just seems a little high. I don't know if you compare any other transitions. If it's like hydrogen bonding, it might be 10 kilojoules per mole.
Okay.
For your rearranging. So maybe you want to compare that with some other ice transitions.
Yeah, like ambient pressure.
It's just
Good
just
suggestion.
ordering might be a little high.
Yeah. Okay. Good suggestion. Yeah, Raja.
The high frequency changes, like your changes is not from your electronic circuit.
How to do what? I understood the second, but how to do what?
In the high frequency region, you
Yeah.
have a lot of error, right?
Yeah.
Body side.
Yeah.
So how do you eliminate that if it's not due to electronic interference or something? The oscillations.
Well, the blue points, actually, the error bars aren't so large. And those were the highest driving voltage. So that's really the simple way, is drive the voltage. I think in this case, that was causing, let's see. Okay, so let's take at 100 kilohertz. So 100 kilohertz. I'm driving enough power. I mean, it's only 26 milliwatts, but that's causing a 2 and a bit Kelvin change in temperature at 100 kilohertz. It's also changing like a static temperature rise of 20 Kelvin. So it's non-ideal in the sense Ajay is talking about of the absolute background temperature, but it actually is a pretty small error bar because I'm kind of pushing a lot of current in. So that's the best way. I mean, I've made these heaters as thin as possible, so I'm not going to make it 1 nanometer thick and try to get better signal to noise. Just make a lot of measurements, and then and since there's so much data here, there's amplitude and frequency variations. There are possibilities for more complex modeling of these waveforms. I'm just showing you the first order information, and if I had data across more interesting transitions, I would start modeling it.
Okay. No more questions. Let's thank Zach.
And sandwich time.
Very nice job, Zach.
So fast.
It's a real cliffhanger.
Yeah. What's the magnitude of one side of the cell? That's what this is showing.
But there was a lot of fun. I mean, last year we were actually doing all best degree is red and it's red and I would take that. Typically, another side is less than 10 nanometer, but for no more than less than 5 nanometer. Oh, that's the same. Then it's I wasn't sure about this is what he's doing.
Yeah, I have lots of things to talk to you about. I should probably make a list so I don't forget any of them, but there are a couple.